welcome to this problem walkthrough. Today, we'll explore problem number 540, titled Single Element in a Sorted Array. This is an intriguing challenge that tests your ability to identify a unique element in a sorted array where every other element appears twice. Let's dive in and uncover the optimal solution step by step. In this problem, you're given a sorted array of integers, where every element appears exactly twice, except for one unique element that appears only once. Your task is to find this single element. Importantly, the solution must be efficient, running in O log n time complexity, and it must use constant space. The input is a single array called nums, which is sorted in non-decreasing order. The length of the array is guaranteed to be odd, and every element in the array, except for one, occurs in pairs. The output is the integer that appears only once. Let's look at an example to understand this better. If the input array is nums equals 1 1 2 3 3 4 4 8 8, your job is to identify the number that doesn't have a pair. For the given input, the output is 2. Here's why: the array contains pairs like 1 1, 3 3, 4 4, and 8 8. But the number 2 stands out because it doesn't have a matching pair, it's the lone single element. Now, consider another example. If nums equals 3 3 7 7 10 11 11, the output will be 10. Again, the array is grouped into pairs, 3 3 7 7, and 11 11, but 10 is the only number without a pair. These examples illustrate the core task, identifying the single, unpaired element in a sorted array. Taking another example, if nums equals 1 1 2 2 3 3 4 4 5 6 6 7 7, the output is 5. Here's the reasoning: the array groups into pairs like 1 1 2 2 3 3 4 4 6 6, and 7 7. Among these pairs, the number 5 is the single element that doesn't belong to any pair. The constraints for this problem ensure that the array length is odd, between 1 and 10 to the power of 5, and every number in the array is between 1 and 10 to the power of 5. The array is always sorted in non-decreasing order, and all elements except one will appear exactly twice. These guarantees help simplify the problem and ensure there's always one and only one single element to find. Now, let's discuss some edge cases. First, consider the smallest possible array, nums equals 1. Here, the array contains just one element, so the output is simply 1. Next, think about a scenario where all elements have duplicates except for the first one, like nums equals 1 2 2 3 3 4 4. In this case, the output is 1. Similarly, if all elements have duplicates except for the last one, such as nums equals 1 1 2 2 3 3 4, the output will be 4. Finally, if the single element is located in the middle of the array, like nums equals 1 1 2 3 3 4 4, the output is 2. These examples highlight the variety of situations to consider when solving the problem, ensuring your solution handles all possible cases efficiently. To solve the problem of finding the single element in a sorted array, the first approach we can consider is the brute force method using linear search. The intuition here is straightforward: since the array is sorted and every element except one appears exactly twice, we can simply traverse the array in pairs. For each pair, we compare the current element with the next one. If we encounter a mismatch, it means we've found the single element. If no mismatches are found during the traversal, the single element must be the last element in the array. While this approach is simple to implement and requires no additional space, it has a time complexity of O n, as we might need to examine the entire array. However, this doesn't meet the problem's requirement of O log n time complexity, which is the main drawback of this method. It's a good starting point but not an optimal solution for this problem. A more efficient solution leverages the sorted nature of the array and uses binary search to achieve O log n time complexity. The key observation here is that in a sorted array, the pairs of duplicate elements always align on one side of the single element. This alignment depends on the indices. If the index is even, the current element should match the next one. If the index is odd, the current element should not match the next one. By identifying where this pattern breaks, we can locate the single element. The steps involve initializing two pointers, low and high, at the start and end of the array. We then calculate the middle index and check whether the pattern of pairs aligns as expected. Depending on whether the mismatch occurs on the left or right side of the array, we adjust the search space by updating the low or high pointers. This process continues until the low and high pointers converge, which will pinpoint the single element. This approach is efficient because it repeatedly halves the search space, ensuring logarithmic time complexity. The binary search approach has a time complexity of O log n, as we repeatedly divide the search space in half, and a space complexity of O(1), since no additional data structures are required. While this approach is optimal for the problem's constraints, it's slightly more complex to implement because it relies on understanding the pattern of indices and their alignment. Another alternative worth considering is the XOR approach, which uses the properties of the XOR operation, where a number XORed with itself results in 0. By XORing all elements in the array, the duplicates cancel out, leaving only the single element. This method is simple to implement, requiring just one pass through the array in constant space. However, its time complexity is O(n), which doesn't meet the problem's requirement of O log n. So while XOR is an elegant solution, it's not suitable in this case due to its linear complexity. Ultimately, the binary search approach is the chosen strategy because it satisfies the problem's constraints of O log n, time complexity, and O(1), space complexity. The key insight that makes binary search effective is recognizing the alignment of indices and using this pattern to efficiently narrow down the search space. While the XOR approach is simpler to code and the brute force method is intuitive, neither of them achieves the logarithmic time complexity required. The main advantage of binary search is its optimal performance, but it does come with the trade-off of being slightly more complex to implement. However, by carefully applying the observations about index parity and alignment in a sorted array, we can ensure that this approach is both efficient and correct, making it the most suitable choice for solving this problem. The problem involves finding a single unique element in a sorted array where every other element appears exactly twice. What makes this interesting is the constraint to solve it in O log n, time complexity. This eliminates straightforward linear scans, guiding us towards binary search as the optimal approach. The sorted property of the array, combined with the fact that elements appear in pairs, allows us to use a clever observation. Depending on whether the unique element is to the left or right of the midpoint, the pairing pattern in the array will change. To start, we initialize two pointers, low and high, to mark the boundaries of our search. The goal is to narrow down the search space iteratively until only the unique element remains, all while leveraging the properties of binary search. The next step is to calculate the midpoint within the current search space using the formula mid equals low plus, high low, // 2. This prevents overflow for large values of low and high. To maintain the pairing logic, we ensure that mid is even. If it's odd, we adjust it by decrementing it by 1. This ensures we always start checking pairs at even indices. Once we have a valid mid, we compare the element at ARR mid with its immediate neighbor ARR mid plus 1. If these two elements are equal, it means the unique element must lie to the right of mid, so we update low to mid plus 2. Otherwise, the unique element must be to the left or at mid, so we update high to mid. This process repeats until the pointers low and high converge, at which point the unique element is located at ARR low. The key insight driving this algorithm lies in the pattern of paired elements. In a properly paired array, the first occurrence of each pair is at an even index, and the second occurrence is at the subsequent odd index. For instance, in the array 1, 1, 2, 2, 3, 3, 4, the first indices of pairs are 0, 2, and 4, all even. However, the unique element disrupts this pattern. For example, in the array 1, 1, 2, 3, 3, 4, 4, the unique element 2 appears at index 2, causing the subsequent indices to shift. This disruption is what binary search exploits, using the pairing pattern to determine whether the unique element is to the left or right of the midpoint. By having the search space at each step, the algorithm achieves O log n time complexity, making it highly efficient. The algorithm operates solely on the input array, meaning no additional data structures are required. Two pointers, low and high, are sufficient to track the search space. Let's consider a few edge cases. First, if the array has only one element, such as 1, that element is the unique one. Next, if the unique element is at the start of the array, such as in 2, 3, 3, 4, 4, the algorithm will identify 2 as the unique element. Similarly, if the unique element is at the end, as in 1, 1, 2, 2, 5, the algorithm will correctly return 5. These examples highlight the flexibility of the binary search approach in handling different scenarios while maintaining its efficiency. Now, if the unique element is located in the middle of the array, the algorithm handles this case seamlessly as well. For instance, consider the array 1, 1, 3, 4, 4. The unique element, 3, is positioned in the middle. The binary search process will quickly locate it by narrowing down the search space based on the pairing pattern disruption. Analyzing the complexity, the time complexity is O log n, due to the halving of the search space in each iteration. The space complexity is O1, since no additional memory is used beyond the 2 pointers. To better understand, let's walk through an example execution step by step. Consider the array 1, 1, 2, 3, 3, 4, 4, where the unique element is 2. We'll initialize the pointers low and high to 0 and 6, respectively. In the first iteration, we calculate the midpoint as mid equals 3. To ensure mid is even, we adjust it to 2. Checking the pair at index 2, we find that ARR 2 is 2 and ARR 3 is 3, which are not equal. This tells us the unique element is at mid or to the left, so we update high to 2. In the second iteration, the midpoint is recalculated as 0. Comparing ARR 0 and ARR 1, we find that both are 1, indicating a valid pair. This means the unique element is to the right, so we update low to 2. At this point, low equals high, and the loop terminates. The unique element is found at ARR 2, which is 2. This step-by-step process demonstrates the precision and efficiency of the binary search algorithm in locating the unique element. This implementation solves the problem using a binary search approach to achieve O log n time complexity. The input is a sorted array where all elements except one appear exactly twice. The goal is to find the single non-duplicate element. We initialize left to 0 and right to the last index of the array. The binary search continues as long as left is less than right. Inside the loop, we calculate the middle index mid using integer division. To simplify pair comparisons, we adjust mid to be even if it is odd. We then check if the element at mid matches the next element, nums, mid plus 1. If true, the unique element must be to the right of mid, so we update left to mid plus 2. Otherwise, the unique element lies at or to the left of mid, so we update right to mid. The loop exits when left equals right, and the unique element is found at index left. This approach ensures logarithmic time complexity because the search space is halved at each step. The code is efficient, leveraging the sorted property of the input array and the guarantee that every other element appears in pairs, making it optimal for this problem. This is the Java implementation of LeetCode problem number 540, single element in a sorted array. The logic mirrors the Python solution, where binary search is used to efficiently locate the single non-duplicate element in a sorted array. Key differences in Java include explicit type declarations and handling Java class structure. The algorithm ensures that the search space is narrowed based on the pairing pattern of elements, maintaining the time complexity of O log n. Here, we are given a sorted array where every element appears exactly twice, except for one unique element. Our task is to find this unique element using binary search. We start with left at 0 and right at 8, the indices of the first and last elements in the array. First, we calculate the middle index using the formula mid equals left plus, right left, //2, which gives us mid equals 4. Since mid is even, no adjustment is needed. We then compare nums, mid, with nums, mid plus 1, which are 3 and 4, respectively. Because these two values are not equal, the unique element must lie on the left side of the array. So, we update right to mid, making it 4. Next, we recalculate mid as 2 and compare nums, 2, with nums, 3, which are 2 and 3. Again, these values are not equal, confirming that the unique element is still on the left side. We update right to mid, making it 2. Now, calculating mid again gives us 1, which is odd, so we adjust mid down to 0 to ensure it is even. We check nums, 0, and nums, 1, which are both 1. Since these values are equal, the unique element must be further to the right, so we set left to mid plus 2, making it 2. At this point, left and right both equal 2, and the unique element is found at nums left, which is 2. This is our result. Now, we look at another example with the input array nums equals 3, 3, 7, 7, 10, 11, 11. Here, we again aim to find the unique element using binary search. Initially, left is set to 0 and right to 6. Calculating the middle index gives us mid equals 3, which is odd, so we adjust it down to 2 to keep it even. Comparing nums 2 and nums 3, both are 7, indicating that the unique element lies to the right of mid. Therefore, we update left to mid plus 2, making it 4. Next, we compute a new mid, which is 5. Since this is odd, we adjust it to 4. We then compare nums 4 and nums 5, which are 10 and 11, respectively. These values are not equal, so the unique element must be on the left side. We update right to mid, setting it to 4. At this stage, both left and right equal 4, and the unique element is found at nums left, which is 10. This is the output for this example. In this final example, we are given the array nums equals 1, 1, 2, 2, 3, 4, 4. Starting with left at 0 and right at 6, we calculate mid as 3. Since mid is odd, we adjust it down to 2 to make it even. Comparing nums 2 and nums 3, both are 2, which means the unique element lies to the right. We update left to mid plus 2, setting it to 4. Next, we calculate a new mid, which is 5. This is odd, so we adjust it to 4 to keep it even. Now, we compare nums 4 and nums 5, which are 3 and 4, respectively. Since these values are not equal, the unique element must be on the left side. We update right to mid, making it 4. At this point, left and right both equal 4, and the unique element is found at nums left, which is 3. This gives us the result for this example. The time complexity of this solution is determined by its use of binary search to locate the single non-duplicate element in the sorted array. Binary search works by repeatedly dividing the search space in half. This means that if the array contains n elements, the number of iterations required to narrow down the search space to a single element is proportional to the base 2 logarithm of n, or log base 2 of n. Within each iteration, the algorithm performs a few constant time operations, like calculating the middle index, checking if the middle element forms a pair with its neighbor, and adjusting the search bounds by updating the left or right pointers. Since none of these actions depend on the input size, their individual time complexities are O1. When you combine the logarithmic reduction in search space with the O1 operations in each step, the overall time complexity of the binary search process is O log n. This remains true across best, average, and worst-case scenarios, because no matter how the data is arranged, the algorithm always halves the search space until the unique element is found. To mathematically verify the time complexity as O log n, we can analyze how the binary search reduces the number of elements being processed. In each iteration, the algorithm examines n/2, n/4, and so on, until only one element remains. The total number of iterations can be determined by solving the equation n divided by 2 to the power of k equals 1, where k represents the number of iterations. Rearranging this equation gives k equals log base 2 of n. This confirms that the algorithm runs in logarithmic time, O log n, with respect to the input size n. Now, for space complexity, the algorithm is extremely efficient. It uses no additional data structures, relying only on a few integer variables like left, right, and mid to manage the search process. These variables occupy a fixed amount of memory regardless of the input size, resulting in an auxiliary space complexity of O1. Since the input array is simply passed to the function and not copied or altered in a way that increases memory usage, the overall space complexity remains O1. When we consider the total space complexity of this solution, it is clear that the algorithm operates within O1 space. This means it uses a constant amount of memory, irrespective of the size of the input array. To better understand the efficiency of this approach, let's compare it to a brute force method. A naive solution would involve iterating through the array and comparing each element with its neighbors to find the unique one. While this approach is straightforward, it requires examining each element individually, leading to a time complexity of O(n). However, it shares the same space complexity as the optimized solution, O1, because no additional data structures are used. For example, in the brute force approach, you would check if nums I is equal to nums I plus 1 for every element until the unique one is found. This works, but it becomes inefficient as the array size grows. In contrast, the binary search method significantly reduces the number of elements examined by leveraging the sorted property of the array. This enables it to achieve a much faster time complexity of O log n, while still maintaining the same minimal space usage of O1. To summarize, the binary search approach demonstrates a time complexity of O log n, owing to its ability to have the search space in each iteration, and a space complexity of O1, as it requires no additional memory beyond a few integer variables. This makes it an optimal solution for the problem, especially for large input sizes. The brute force method, while simpler, is less efficient with a time complexity of O(n), even though it shares the same space complexity of O(1). By taking advantage of the sorted property of the input array, the binary search approach not only reduces the computational effort but also ensures scalability for larger datasets. This balance of efficiency and minimal memory usage highlights why the binary search method is the preferred solution for this problem. When solving this problem, there are some common mistakes to watch out for. First, not accounting for the fact that the array is sorted can lead to inefficiencies. If you use a brute force approach, like linear search, you're ignoring the sorted property of the array, which allows for a much faster binary search solution with O log n complexity. Next, edge cases are critical. Arrays with only one element, or those where the unique element is at the very beginning or end, can easily break your solution if you don't handle them properly. Another common pitfall is assuming the unique element is always at an even index. While this might work for some test cases, it's not guaranteed by the problem constraints. Always verify your logic to ensure it's robust across all possible inputs. Now, let's address a few more common mistakes. Poor handling of index boundaries during binary search is a major issue. For example, if you calculate the middle index with low plus high /2 in languages where integers can overflow, you might encounter bugs. Similarly, if you don't adjust the low and high pointers correctly, you could end up in an infinite loop or skip valid elements. Another overlooked strategy is the XOR property. XOR is a mathematical operation where XORing two identical numbers results in 0, and XORing 0 with any number gives the number itself. Leveraging this property can help solve the problem in O(n) time without additional data structures. However, remember that while efficient, this approach doesn't leverage the sorted property of the array, so you might opt for binary search in interviews to achieve O log n. When tackling this problem in an interview, there are a few key insights to keep in mind. Because the array is sorted, binary search should immediately come to mind as an optimal strategy, since sorting often hints at logarithmic solutions. It's also important to fully understand the problem constraints, specifically, that the unique element is the only one without a duplicate. This allows you to narrow down your approach. A crucial skill here is pattern recognition. With binary search, you'll want to focus on the half of the array where the unique element could exist, rather than wasting time checking unnecessary elements. Additionally, interviewers often value your ability to explain trade-offs. For example, you should be able to articulate why binary search is preferred over an XOR-based solution for larger arrays. Finally, always communicate how you've tested your solution against edge cases, like single-element arrays or cases where the unique element is at the last index. This demonstrates thoroughness in your problem-solving approach. This problem also has parallels with other related problems, which can help you recognize common themes. For instance, in LeetCode 136, single number, you need to find the single number in an unsorted array where every other number appears twice. The XOR property is key to solving that efficiently. Then there's LeetCode 540, the problem we're discussing here, which requires binary search for optimal performance in a sorted array. LeetCode 260, single number 3, is another variation where you're tasked with finding two non-repeating elements in an array where every other element appears twice. This requires a combination of XOR and bit manipulation. Finally, LeetCode 137, single number 2, involves finding the single number in an array where every other element appears 3 times, which requires even more advanced bit manipulation techniques. Familiarity with these problems can deepen your understanding of how to approach similar challenges. There are multiple approaches to solving this problem, each with its own trade-offs. A brute force solution using linear search has O(n) complexity and is simple to implement. However, it's inefficient for larger inputs and doesn't utilize the sorted property of the array. Using a hash map is another option, offering O(n) time complexity, but it requires O(n) space to store the counts of elements. The optimal solution is binary search, which achieves O log n complexity by leveraging the sorted property of the array. This approach is highly efficient but requires careful handling of boundary conditions to avoid errors. Finally, there's the XOR approach, which runs in O(n) time and O(1) space. While it's both fast and space efficient, it doesn't take advantage of the sorted property, making it less optimal for this specific problem. Understanding these trade-offs is essential for selecting the best solution based on the problem constraints. Great job following along. We've successfully solved this single element in a sorted array problem by leveraging binary search for optimal performance. Remember, understanding the problem's constraints and utilizing efficient algorithms like binary search are game changers in coding interviews. Thanks for watching, and don't forget to like, subscribe, and keep practicing. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!